So next we're going to say about network dynamics such as structural models, cascading behavior in networks. The information about cascades. When people are connected by a network, it became possible for them to influence each other's behavior and decisions. There are limitless set of situations in which people are influenced by others. Opinion they hold, products they buy, political position they support, activities they pursue, etc. Many things so that the people are influencing. Diffusions of innovations. The diffusion of innovation is a theory that seeks to explain how, why, and what rate the new innovation and new idea are being spread. Analyzing the group formation and evolution, there are three different factors that is being involved: membership, growth, and change. The membership, what are the structural features that influence whether a given individual will join a particular group? Growth, what are the structural features that influence whether a given group will grow significantly, that is, gain a large net number of new members over time? Change, a given group generally exists for one or more purposes at any point in time in our dataset. For example, the groups are focused on particular topic of interest. How do such focus change over time, and how these changes are correlated with the changes in underlying set of group members? So here there are two images that are available which indicates the probability of P joining a live journal community as a function how the other friends as a K already joined in the particular community. The error bars are represented in two standard errors. So the figure 2, the probability of P joining DPLP community as a function of a number of friends how K has already joined in the community. The error bars are indicated in two different standards. That is a positive error which protrude and the negative error which diffused. The negative error indicates that persons are leaving the community. The positive error is how many new people are joining into the community. The game theory and model of diffusions. So based on the two-player coordination game, each node has a choice of two possible behavior, the A, an old behavior, and a new behavior. B, a old behavior, and B, a new behavior. If a node V and W are linked by age, that there is an incentive for them to have their behavior match. Represented as a game in which V and W are players, A and B are possible strategies. So define the payoff as follows. If both V and W chooses a behavior A, they will receive the payoff of Q. If both V and W choose the behavior B, they will receive the payoff of 1 minus Q. If both receive the opposite behavior, they will receive the payoff of 0. In the network at large, each node V plays a copy of a game with each of its neighbor. The payoff of the node is equal to sum of the payoff of the player at each edges. So here is the representation. If A acquired A, then the payoff will be Q comma Q. If A attracts the opposite B, then the payoff will be 0 comma 0. If B acquires the A, then the payoff will be 0 comma 0. So B acquires B, then the payoff will be 1 minus Q comma 1 minus Q in terms of V and W. The question faced by V are, suppose some of the V neighbor adopts A and some adopts B. So what should we do maximize its payoff? Let's V have the DV neighbors and DV of A of its neighbor adopts A. The DV of B has adopted B, then if we chooses A, the payoff will be equal to QDV of A. If you chooses B, the payoff will be 1 minus Q dV of B. Thus, we should understand we should adopt a behavior B of if dV of A is greater than Q dV, and the behavior A if dV of B is less than Q dV, or P is greater than or equal to B divided by A plus B. Let us just put it to the simple example. The left side is the A, the right side is B. Then it is being adopted to the V. The node V must choose between the behavior whether it's going to choose A or B. So what its neighbor are being doing. The cascading behavior. In any network, there are two obvious equilibria to the network-wide coordination game. Everyone adopts A, everyone adopts B. We want to understand how easy it is to tip the network from one of these equilibria to other. What other immediate equilibria look like the state of coexistence when A is adopted in some part of the network and B is adopted in. The cascading behavior as an example, suppose everyone in a network initially using B, then the smallest set of initial adopters all decide to use A. For example, in a classroom, there are two persons are standing for a class representative. The 80% of the class strength has been adopted A. The certain people that remaining 20% will definitely adopt B. So due to that, that is a small set world phenomena. The small world phenomena we'll be seeing over in the next topic here. Some of the neighbors has initially adopted may decide to swap. Here the human brain's tingling, swapping. There are few peoples will be swapping between A and B. The A then some of the behavior may switch and some fourth is potentially cascading the patients. So when does this result? Every node eventually switch to A, and when isn't the result, what causes the spread of A? The coordination game setup A is equal to 3, B is equal to 2, the P is equal to B divided by A plus B. The value will be 2 by 5. The first diagram represents the underlying network. The second diagram represents the two nodes of the initial adapter such as V and W. After one step, two more nodes have been adapted such as R and T. After the second step, everyone is being adapted as there is only 1, 2, 3, 4, 5, 6 members are being there in a particular network. Consider another set of example in the coordination game setup. The A is equal to 3 and B is equal to 2. So that the Q will be 2 divided by 3 plus 2, that is B by A plus B. The 2 divided by 5. Thank you. So next we are going to see about small world phenomena. So in the previous lectures we have seen how the social networks can serve as a conduit by which the ideas and innovation flow through a group of people. To develop this idea more fully, we now relate it to the another basic structural issue, the fact these groups can be connected by short path through the social network. When people try to use a short path to reach others who are socially distanced, they are engaging in kind of focused search that is much more targeted than the broad spreading pattern exhibited by the diffusion. The diffusion is spreading in all the ways by all means of thing. Here there is being structural behavior how the spreading we are going to study how the spreading is being happened. For example, in a social network I am linked with 100 friends. These 100 friends is linked with another individually 100 friends. So the linking will goes like a 100 1 to 100 and 100 to individually 100. So, understanding this relationship between the targeted search and wide range diffusion is important in thinking more generally about the way the things flow through the social networks. So, this is called a small world phenomena or sixth degree of separations. Here, we are going to take a simple example. Let's start with a model for existence of short path. Should we be surprised that the path between seamlessly arbitrary pair or the people of short? The figure, this figure, which is what you are seeing, shows the basic argument suggesting that short paths are least compatible with intuitions. Suppose each of us know more than 100 people on a first name basis, then taking into account the fact that each of your friends have at least 100 friends other than you. You could in principle two ways make a more than 100 into 100, that is 10,000 peoples. Taken into the account the 100 friends of these people bring us to more than 100 into 100 into 100. It's more than 1,000,000 people. That is a 1 million people who is in principle could be the three-way step away. In other words, the number or growing power, the power of 100 with each step bringing us to the 100 million after 4 steps and 100 billion after 5 steps. So you are being connected with your friends and your friends are connected with the friends of your friend. The social network expands to reach many people in a few steps. Purely exponential growth produces in a small world. That's a spreading is in terms of small world phenomena. So next we're going to see that is the previously we have seen only a homogeneous behavior of a group of friends. For example, your friend, the two of your friends are having a mutual friends, so it's somewhere our numbers is getting shortened. That is due to the interlocking behavior of your friends. That is called as so-called the triadic closure in a social network work to limit the number of peoples you can reach by following a short path. So it is a contrast between the previous figure and this figure so that the total reachable quantity of the people will get reduced due to the triadic closure in social networks. So that what makes the small world phenomena surprising to many people when they first hear it, that social networks appears from local perspective of one individual to highly clustered, not a kind of massively branching structure that would be obviously reach many nodes along with short path. There are various models to study this small world phenomena. That is being out of scope for our syllabus. You must know the basic thing, the Watt-Strauss model, and then decentralized search model. So how we search the data in a decentralized search thing. So there are different models are available. So these models are called as small world phenomena in which data will drive through the certain group of people through social networks. Thank you.